Today we are looking at section 3.4, so we're talking about mostly piecewise defined functions, but in preparation to do that, they also have what they're calling a library of functions. So these are just your parent graphs that you should already know from previous courses. In Algebra 2, there was a huge focus on all of these parent graphs. So I cut and pasted most of the information here from the text, and we are going to add in one more, which is the reciprocal function. So the parent function for the reciprocal function is 1 over x. So when I go to graph 1 over x, the x values that I use are 1/2, 1, and 2. 1 divided by 1/2 is 2, so 1/2, 2 is my first point. Then when x is 1, y is also 1. And then when x is 2, y is 1/2. So it gives me these 3 points, which creates a function that kind of hugs both axes. So it's got an asymptote on both sides. If I have negative x values, if x were -2, that would give me negative 1/2. If x is -1, y is also -1. And if x were -1/2, that would give me y equals -2. So that gives me a matching branch on the other side. So the domain for this, what can x be? Well, I've got an x in the denominator, and we know that x can't be 0. So that means my domain in interval form would be -infinity to 0, 0 to infinity. So we're skipping over that undefined value of x equals 0. The range does the exact same thing because our values approach a y of 0, but they never actually get there. So in this case, the domain and the range are the same for this particular parent function. Increasing intervals, meaning as I'm moving from left to right, when are the y values increasing? And that is never. Because over here, my values are getting smaller, and over here, values also getting smaller. So it is never increasing. It is decreasing for all of its domain. So from -infinity up to, but can't include 0. And then from 0 to infinity, also decreasing. The last thing that they've listed for all of these types of functions that we should know is whether the function is even, odd, or neither. So you can see this one's neither, odd, even, so on and so forth. That's based on the symmetry here. So this is symmetric about the origin, which means it is an odd function. So make sure that you know your parent graphs. Make sure you know what the equation looks like and what the graph associated with it looks like. So absolute value parent graph, and then we've got all these others as well. Sometimes in the text, the book will call the standard quadratic function just a square function. Obviously because it's x squared, but quadratic, square, those are the same thing if you happen to see that and catch that in the text. So the rest of the section is based on piecewise defined functions. So in example 1, we're given the function and we're asked to find some individual values. So what this is first deciding which piece I need to plug the value in to, and then actually doing it. So f of -1. So when I look at my domain restriction here, that's what this right side of a piecewise function is called. It tells me for which x values I should be using that piece. So my top piece, I should only use, sorry, bless me, if x is between -2 and +1. So I look at the value given, Negative 1 is between negative 2 and positive 1. So that means I'm going to use the top piece here. And so then all I do is I plug in negative 1 to that function rule. So x cubed is now negative 1 cubed, which, of course, gives me negative 1. So f of negative 1 is negative 1. Now, f of 1, be careful here because I've got a 1 here and a 1 here, and it matters which one I use. So you have to look at which one it is defined for, and that means which of those pieces does it have the equal sign for, and that'd be this one. This says strictly less than 1, not equal to 1. So it's not the top piece, it's the bottom piece. But then we just do the same thing, but with the rule that's on the bottom. In this case, 3 times x, which we're plugging in 1, plus 2 is the rule. So 3 times 1 is 3, plus 2 is 5. So f of 1 equals 5. Last one for this example, f of 3. 3 falls in this interval. It's between 1 and 4. So this one, I should also use the bottom piece, which means I plug into the bottom rule only. So 3 times 3 plus 2. I'm putting in this 3 in place of that x. So 3 times 3 is 9, plus 2 is 11. All right. Next, we are introducing, which this may be new for some of you. It may have been in honors algebra 2, not in regular, and it's probably in pre-calc if you've taken pre-calc. But if not, this might be new to you, so I'm going to explain this. This can also be written like this. It's like a set of 2 brackets. So these mean the same thing when you've got 2 brackets or you've got an INT. What this is it's called a greatest integer function. And what a greatest integer function does is it assigns, and I'm going to draw a number line here because this is going to help us, but it assigns the function's value to the greatest integer that number has gone past on the number line. So all of our examples here are between -2 and +2. So I'm going to draw a number line that covers those values. This is going to help us figure it out. There is a greatest integer button on your graphing calculator, by the way. So if you can find that, you can check your answers as well. So f of 1.2 means the greatest integer that 1.2 has passed on the number line. So as I'm going, 1.2 would be about right here. The greatest integer that I've gone past is 1. But my function here has 1 over 2. So now I have to divide that. So the greatest integer of 1.2 over 2, so now f of 1.2 means greatest integer of 1.2 over 2. So hopefully that first example helps you determine how greatest integer function works. Now we're actually going to do this problem. So 1.2 divided by 2 is 0.6. So greatest integer function of 0.6. So going, 0.6 would be right here. The greatest integer that it's gone past is 0. So that would be my answer. Now I have 1.6. Again, that means I'm plugging it in here. So greatest integer of 1.6 over 2. 1.6 divided by 2 is 0.8. So greatest integer of 0.8 Well, 0.8's right here. It's past 0.6, but it still hasn't gotten to 1. So still the greatest integer that it has passed is 0. Now greatest integer function when I'm plugging in negative 1.8 for x. So greatest integer, negative 1.8 over 2. So negative 1.8 divided by 2 is negative 0.9. Negative 0.9, when I graph it on the number line, is right here. The greatest integer that it has gone past is negative 1. So I always get people that are like, oh, well, just round it down. Well, then now when we've got negatives, it works a little bit differently. So the number line example will always work. Just so if you've never seen that function before, you hopefully understand it a little bit better now. All right, in example 2, we're given a piecewise function, and we actually want to find domain, intercepts, graph it, and show the range. So for domain, you can look at what your domain restriction is. That should give you your answer when you combine them. So this goes from negative 3 to 0. It's not defined at 0 in this piece, but it picks it up here. So we've not actually taken any gaps. We go all the way to 2, including 2. And then this picks up where it left off. And greater than just means toward infinity. So that means my lowest value is negative 3, including because it has an equals. And there is no upper limit because it's just strictly greater than. So from negative 3 to infinity is going to be my domain. If you prefer to do the domain after you graph it, you can do that. It's just if you mess up the graph, it might mess up your domain. Intercepts, you can also do with the domain restriction, at least for the y-intercept, because when you plug in 0 for x, you know what piece you're on. That's the second piece. So when x is 0, I'm in the second piece, and y happens to be 5. So 0, 5, I know is my value for the y-intercept. I'm going to look at the graph to figure out my x-intercept because I need to know what side of the axis I'm on to know which piece I need to use. So when I go to graph, you must make a table for each piece. Including all boundary values for x. So here's what I mean by that. I am going to list for my top piece 3x plus 5, and it's when x is between negative 3 and 0, not including 0. But it doesn't matter that it's not including 0. 0 still has to be included in my table. It doesn't matter if it has an equals or not. I should probably pick something in between there to figure out what I want. So let's say I'm going to pick negative 1 maybe. We could pick negative 2 also if we wanted to. To figure out the y's, I plug them in here. So negative 3, I plug in. 3 times negative 3 is negative 9. Plus 5 gives me negative 4. Then 3 times negative 1 is negative 3. Plus 5 is 2. 0. 3 times 0 is 0. Plus 5 is 5. Once you have your points for all boundary values, you should either write closed or open based on whether it has an equals or not. Anything that is not a boundary value is automatically closed. So you don't have to write closed here, it's automatic. So now I can plot these points. This with a closed circle, this with a closed circle, this with an open. So negative 3, 4. So left 1, 2, 1, 2, 3, up 1, 2, 3, 4. Then negative 1, 2. Oops, I plotted that first point wrong. Good thing I caught that. That would have been a nightmare on video. Negative 3, 1, 2, 3, 4. There, now we fixed it so you won't be confused. 0, 5 should be an open circle. 1, 2, 3, 4, 5. Open circle. When I finish this piece, I should always connect the pieces. There's nothing below negative 3. So I don't need an arrow down there. It stops. So that's it. Now, my middle piece, I'm okay. You should know that's just a value. F of x equals 5, that's a horizontal line. So I'm okay with no table there. That's a horizontal line where y is 5. So you can then make as many points as you want, but it has to follow the boundary. It goes from 0 to 2. So 1, 2. And notice I actually have to close in this open circle because it's in the exact same spot. And when a closed and an open circle battle, the closed circle always wins. So that circle is now closed. My bottom piece, x squared plus 1. So this is only when x is greater than 2, so I have to include that boundary value. And then I need some others, so maybe I'm going to pick 3. If you need more, you could pick more, but this is going to be an open circle. When I plug 2 into this rule, 2 squared is 4, plus 1 is 5. And then when I plug in 3, 3 squared is 9, plus 1 is 10. So open circle at 2, 5. That's the same point that's already closed. Again, when open and closed circles fight, the closed circle always wins, so it's going to stay closed. Now I need a closed circle at 3, 10. So 1, 2, 3, all the way up to 10. And it's a parabola. Don't draw it with a line. You should know from Algebra 1 that x squareds make parabolas. If you didn't, it's right here in your parent graphs, so you should know the shape that it makes. So now that I can see it, I can see that I should have an x-intercept, and it's definitely to the left of x equals 0, so that means it's my top piece. So when I plug in 0 for y, it's in that piece. So when I solve this, subtract 5, divide by 3, I get x equals negative 5/3. So to finish my intercepts, my x-intercept there is negative 5/3, 0 for part B. So A, B, and C are done. Last part is the range. So the lowest value I see for y is this point here, which my table told me was negative 4. My highest point, there's no gaps because these open circles got closed in, and there's an arrow. So negative 4 to infinity. All right. Last one is kind of the working backward of example 2. We not only need to be able to graph our own piecewise functions, but we need to be able to write equations for piecewise functions as well. Both of my pieces here look to be linear, which those are pretty easy to write. I know the copier isn't always number 1, but just so you know, this guy is an open circle there. So I am going to, next to each of these, because they're both lines, that means my rule, I should be finding a slope and a y-intercept, because y equals mx plus b. So this guy right here, this piece, I can see that I've done a rise of 2 units and a run of 1 unit. So that means my slope is 2. I also happen to be given the y-intercept. It's 2. So that makes my job pretty easy here. If I want to write my piecewise function, I can do f of x equals, for my top function, the rule y equals mx, so 2x plus b, which is 2. So that's the rule. Now I figure out what my domain restriction is. This piece has 2 closed circles. The domain restrictions, take a look. It's always the x values. I'm not looking at the y coordinates. This x goes from -1 to 0. So -1 is the lowest, 0 is the highest. They both get equal signs because they were both closed circles. Now I'm going to go and look at my other piece. So from here, I can count my rise and run if I want this way. So rise 2, run 2. So m rise over run is 2 over 2, which is 1. My y-intercept, where it would touch the y-axis, is at 0. So y equals 1x plus 0 is just y equals x. So the rule here is just y equals x. The values of x, it starts at 0, but it's an open circle, which means don't include the 0. And then it has an arrow. So that means keeps getting bigger. So for x is greater than 0 would be my rule. Please keep in mind that you can have pieces like we did in example 2 where it's not always a line and you might have to write an equation of a parabola or something like that. Also keep in mind, like we saw in example 2, if you have a horizontal line piece, it doesn't get an x. This doesn't say 5x. It just says y equals 5. So any horizontal line pieces, there should be no x in the rule. All right. I think that those examples should give you a really good start for your 3-4 practice, and we will answer whatever questions you have when I see you next.